everyone. In this video we're going to talk about horizontal asymptotes. And horizontal asymptotes allow us to answer this question that I've written here. What happens when your inputs are really big? So in our previous videos we've considered the behavior of functions when our inputs get really close to a particular number. And we just talked about that behavior as a vertical asymptote. But now we're going to ask ourselves, what happens when our inputs go off to infinity or get arbitrarily large? And if our inputs get really large and then our outputs get really close to something, like they get really close to 7 or 0 or 100, we're going to call that behavior a horizontal asymptote. So in this video we're going to look at 3 different examples because there's pretty much 3 things that can happen when you're thinking about horizontal asymptotes. So let's start with this example. Let's take a function f of x, which is x divided by x squared plus 2. And what we're going to do is think about what happens when x gets really, really big, or when our inputs get really, really big. And I'm going to notate it this way, as x arrow infinity. So when you see this notation, x, and then this arrow pointing to infinity, it says when x gets arbitrarily large. So as x goes off to infinity, we want to know what happens to our function f of x. So this would be a good opportunity if you wanted to play around, to pause the video, and just plug in some really big numbers for f of x, like 100, a billion, a trillion. You can use Desmos for this. Just see what's happening to our function as x gets really, really big. Okay, so what you should have found is that when you plug in really big numbers into this function f, your outputs actually get really small. In fact, they get so small, they get as close to 0 as you want. So why is that? Well, what I want to do is come over to our function, and I'm going to circle some terms here. Okay, so I'm going to circle this x, and I'm going to circle this x squared. So these are pretty simple polynomials, but these are the leading terms for our polynomials. So the x in our numerator it's the only term there, but it is in fact the biggest term. And then in our denominator, the x squared is also our leading term. It's much bigger than the 2. So when x gets really big, x squared is going to be much bigger than 2. So the 2 really doesn't matter when x is big. And this is going to hold true for all the different rational functions. When we're thinking about really, really big inputs, we're only going to care about the leading terms of our polynomial. All right, so with that said, if I'm only considering my leading terms, this x and this x squared, well, when x is really big, my x squared is going to be much, much bigger than x. And so, well, I'm dividing some number by something that's much, much bigger, and so that's going to tend to 0. So take a number, divide by something that's much bigger than it, you're going to get something that's much smaller. Okay? So as x goes off to infinity, what we notice is f of x goes to 0. So as x gets really big, or as our inputs get really big, our outputs go to 0. So we would say that this function has a horizontal asymptote which is the line y equals 0. So whenever the degree of our denominator is bigger, we're going to have a horizontal asymptote at y equals 0. Okay? So there are 2 other cases. What happens when our degrees are the same, and what happens when the degree of our numerator is bigger. And so I'm going to clean this up, and we'll talk about those 2 situations. Okay, so here's another function to consider. G of x is equal to 6x squared plus 2x plus 1, all divided by 2x squared plus 3. So in the previous example, we saw that when the degree of the denominator is bigger, our outputs are going to tend to 0. But we can't actually use the same argument in this case because when I consider what's happening here, well, my leading term in my numerator is 6x squared. The leading term in my denominator is 2x squared. So when x gets really, really big, I can't say that one of these is much, much bigger than the other because they're both growing at the same rate. They have this square term. So they're not going to be much, much bigger. In fact, they're going to be, pretty close to one another. So what I have to do is a little trick here to think about this. What I'm going to do is multiply the numerator and denominator by 1 over x squared just to see what's going to happen. Okay, so I'm going to take 1 over x squared, I'm going to multiply it through in my numerator. I'm going to take 1 over x squared, I'm going to multiply it through in my denominator. Now I picked this in particular, 1 over x squared, because that's the leading term, right? So the degree of this is 2, so I'm going to divide by 1 over x squared. And so when you do this, what you notice is 1 over x squared times 6x squared is just going to be 6. And then 1 over x squared times 2x. So if I take this 1 over x squared right here, multiply by this 2x, one of the x's will cancel out. And what you're left with is plus 2 over x. And then multiply by 1 is just plus 1 over x squared. And then if I do the same thing in the denominator, the x squareds are going to cancel in the first term, and I'm going to be left with plus 3 over x squared. Okay. So by doing this, it allows me to look at this form of the function. Now, it might look much worse, and I agree it does, but it allows us to think about the behavior. Okay, so we're going to ask ourselves this again. As x goes to infinity, so as x gets really, really, really big, what happens to g of x? Okay, so as x goes to infinity, what happens to g of x? Let's give ourselves another color here. I'm going to underline this. So as x goes to infinity, what happens to this term right here? What happens to 2 over x? Well, I'm going to take 2 and I'm going to divide by really big numbers, so this thing goes to 0. Well, if I take 1 and I divide by a really big number, this thing's also going to tend to 0. And well, 3 divided by x squared, 3 divided by really big numbers is also going to tend to 0. So as x goes off to infinity, most of these things go away, and I'm just left with a 6 and a 2 in my numerator. Okay, so as x goes to infinity, g of x goes to 6 divided by 2, which is 3. So we would say that we have a horizontal asymptote at y equals 3. Okay, so 6 and 2 weren't particularly important here. They're just the leading coefficients for the polynomials. Right? So it's the 6 is the leading coefficient for my numerator polynomial, and 2 is the leading coefficient for my denominator polynomial. So if they were different, really all I'm looking at is the ratio of my leading coefficients. Okay, so when your degrees are the same, you're going to look at your leading coefficients and look at their ratio, and that's going to give you your horizontal asymptote. Okay, so a horizontal asymptote here at y equals 3. So the last situation that we have to consider is what happens when the degree of our numerator is bigger. Okay, so here's our last example. Our rational function is x cubed plus x squared plus 1, all divided by x plus 5. All right, so as we did in the other examples, I am going to take a look at my leading terms. So in my numerator, the leading term is x cubed. In the denominator, my leading term is x. So what we'll notice is the degree of the numerator, which is 3, is bigger than the degree of the denominator. Now, as x gets really big, what happens? So if you're not sure, this is a good place to pause and just plug in some big numbers. Use Desmos, try it out. Okay, so as x goes to infinity, what happens? All right. So what you should have found is that as x goes to infinity, your outputs get really big. So as your inputs get really big, your outputs also get really big. So the reason for that is because, again, these leading terms. When x is really, really big, x cubed is much bigger than everything else. So I'm taking really big numbers, but I'm dividing by something that's smaller than it. Okay, so I take a really big number and I'm dividing by something that's much, much smaller. So this is actually going to grow at a quadratic rate. So x cubed is 2 degrees bigger than x to the first power. And so we know that this quadratic growth is going to go off to infinity. So as x goes off to infinity, r of x, our outputs, also goes off to infinity. And so what we say here is that there is no horizontal asymptote. So the behavior of our function, a rational function with really, really big inputs, there's 3 different things that could happen. We saw the first one was when our denominator has a bigger degree, the horizontal asymptote is 0. When they have the same degree, you look at the ratio of the leading coefficients. And when the degree of the numerator is bigger, we're in this situation where we have no horizontal asymptote. So I hope this video helped out. I'll see you next time.